Okay, so now we're back on part 2 of Rate In and Rate Out. Hi, I'm Mrs. Allen and getting ready for the AP exam here. And first problem we're looking at here now, here's our table of h of t again and our L of t function, where h of t and L of t are both rates. H of t is the rate of the water going in the kiddie pool, and L of t is the rate of the water leaking out of the kiddie pool. So with this one, and maybe I should reflect back on the problem just to show you this is the problem we're still working on, rate in, rate out. Okay, and this is part 2 of this work. So we want the first problem, we want to estimate h prime of 2. So what I'm going to do is I'm going to remind myself that h of t is gallons per minute, and then h prime of t is gallons per minute square, like the acceleration, the rate of change of the rate. So if I look at this, because h is differentiable, then that means it's continuous. So that means somewhere in between 3 and 1, I'm going to say that there's a 2 in here somewhere. So if I want to know what h prime of 2 is, I can kind of go around it. Okay, and I can get the change of h and over here the change of t. So I say h of 3 minus h of 1, and h of 3 is 5, h of 1 is 13. And then that's over 2. So I get negative 8 over 2. And so it's negative 4 over 1. Sorry about that. Negative 4 gallons per minute squared. Okay, and there is your answer here. Okay, everybody good? Moving on. All right, is there a time t from 0 is less than or equal to t is less than or equal to 4 when the rate at which the water is being poured into the pool is equal to the rate at which water is leaking from the pool? Explain why or why not. So again, I'm going to go back to the fact that I have a function that's differentiable, h of t, and so is L of t. And I'm going to look at this, I'm going to say, okay, well, if I start, it's on the interval from 0 to 4, h is differentiable. If I start at 0 and just take a look at what values come out. So I'm going to let w prime of t equal the difference between the rate going in and the rate going out, h of t minus L of t. And I'm going to say, what is w prime of 0? Let me make this a little bit bigger. So it's equal to h of 0 minus L of 0, right? Now, we know what h of 0 is. H of 0 is then 30. From the table, I could scroll back up there, boop, right there. H of 0 is 30. And L of 0, so this is equal to, I'm just going to go this way, 30 minus, and then L of 0, if you look at the function, L of 0 is just going to make that value 0. So now we know that w prime of 0 at one end of the spectrum, on the beginning of the interval, we have our gallons per minute. Our gallons per minute, sorry about that scrolling, is going to be 30 gallons per minute. Okay. So now let's look at the other end of the spectrum, because all I'm doing is really testing some values. Since I know the function is continuous, I want to see what the values turn out to be, because I know down deep inside, if these are the same, and I guess I should have said this, let me digress a little bit. I know that if these two are the same, the rate pouring in is equal to the rate leaking, then I know that h of t minus L of t will, of course, have to be 0. They'd be the same then, because h of t would have to equal L of t then, okay? So I want the difference to be 0, right? Well, right now I know the difference at 0 is 30 gallons per minute, okay? So now if I try the other end of the spectrum, let's try at 4. So I have w prime of 4, and that's going to equal h of 4 minus L of 4. And what is that equal to? H of 4, if you go to the table, it looks like it's equal to 4. So 4 here. h of 4, sorry, h of 4 is 4, minus then L of 4 at that point. It looks like it's 20. I think it's 20. Let's just double check this. Here's our function up here. If I say 25 times 4 over the square root of 16 plus 9, don't I get 100 over the square root of 25, which is 5, and I get 20. So coming back down here, then I get 4 minus 20, which is negative 16 gallons per minute. Okay, now when a rate is positive versus a rate is negative, that tells you some information about it. So at 0, the rate is positive, so that means that the amount of water is increasing, versus the rate at 4, the amount of water is decreasing, 16 gallons per minute. So what happens between a 30 and a 16? Well, we know that. So the way I can conclude this, I want the difference to be 0 so that these two rates are equal to each other. So all I have to say now at this point is, since negative 16 is less than 0, which is less than 30 by the intermediate value theorem, I'm going to do an abbreviation, intermediate value theorem, there exists, I'm going to use the backwards E, a T, there exists a T such that H of T is equal to L of T. Can I get it all in there? And there you have it, L of T, okay? So there has to be a place, because if you have a rate that's negative 16 and a rate that's 30, by golly, then you have to have a place in between the negative 16 to 30. It's kind of like if you have a velocity in a car and you're going 65 and then somehow magically you end up at 85 miles per hour, then you had to pass through all those values between 65 and 85 to get to 85. So the same thing is true here. If it's 0, you're at 30, and then somehow you go down to a rate of negative 16, you have to pass through 0. So there it is. And that's by the intermediate value theorem. So that's pretty important that you state that. All right. The pool can hold at most 200 gallons of water. At t equal 4 minutes, the hole in the pool is fixed. So there's no more water that's going to leak out. But water continues to fill the pool at a rate of h of t. Set up, but do not solve an equation, I love that, involving one or more integrals that could be used to find the time w, when the pool first begins to overflow. So what I have here is kind of what I had in the other problems, that I start with, I have an amount in the pool. I start with 120. I fill a certain amount, and notice I have a question mark there. And then I subtract out what is leaking. But I stopped at 4. Notice I put a question mark there, but I'm going to put a W there now. That's going to represent the time, W, when the pool first begins to overflow. So 200 is where I want to go. So if I take what I start with, I fill it, and I subtract what I leak, then the equation would look something like this. I want that to equal 200. And since it's an equation, not an inequality, I'm going to leave it like that. So now it says the pool can hold at most 200 gallons of water. Sorry about that misspelling. Boop, boop. At t equal 4 minutes, the hole in the pool is fixed. And that represented by this amount that's leaking out. Set up, but do not solve, an equation involving one or more integrals. So you really could see that with this one leaking integral, we could probably put the 50 in there, and we would only have just the one integral here that you see here for the amount of water that's filling the pool. And then you have the number 120. So that's it, folks. That would be your equation that answers the question. Then we have the next one, which is L prime of 2. It's the rate of change. L prime of 2 is approximately to 4.8. So using correct units, interpret the meaning of its value in the context of the problem. So for this one, L prime of 2 is the rate of change of the rate. So being the rate of change of the rate that the water leaks out of the pool is increasing because it's positive. So the rate, and I guess I should say, the rate is increasing the rate is increasing at a rate of 4.8 gallons per minute squared. At t equals 2 minutes, right? At t, 2, and the units on there are minutes. And that's it for that problem. Okay, just recognizing units and what the meaning of L prime of 2 is in that case. Oh, wait, hold it. Is the rate of change of the rate of the water leaking out? I have to be a little more specific. Leaking. The rate is then increasing at a rate of 4.8 gallons per minute squared at t equals 2 minutes. Okay. Alrighty. So last problem, and this is a calculator active problem. So I'm going to go to the calculator on my iPad. I have a mock TI-84 or 83 or something like that. But the rate the hose water is entering the pool can also be modeled by a function. So now this is not an approximation that we're doing. We use the table h of t at first. We're saying is equal to E of t, and it's measured in gallons per minute. Using this model, at what time t is the amount of water in the pool the greatest, right? So here's our amount of water. Now I'm going to let W of t equal the amount of water. And so what you have is what you start with, what you fill, and then what leaks out. So you have those three. And we don't know what the t is at this point. T is just going to be a variable. So it looks like the kind of fundamental theorem problems. So using this model, at what time t is the amount of water in the pool the greatest? So when do we find the maximum values? So what we're going to do is we're going to say, all right, first of all, here's my function. We know at 0 that the gallons in there is 120. And we know that it can only, at some time, we don't know what it is, at the end, it can only go to, and we want to know at what time t is the amount of water in the pool the greatest. So we just want to know what the time is. We know that it can only go to 200, right? So in our equation, what we're going to do is we're going to look at our endpoints. Oh, and it's only from 0 to 4. From 0 to 4. And I think that's missing from the problem, but we're only looking on the interval from 0 to 4. So what we're going to do is we're going to say, well, when do we find a max? We know that at time t equals 0, that it's a certain amount, and time t equal 4, we know what the value is. We know at times t equal 4, we can find that. And so we're going to make a little table. And we have our endpoints here. And at time t equal 0, we have 120. At times t equal 4, we have 109. I'm going to leave it up to you to figure this out because you're just going to use the integral of the expression that you see. And you can use a calculator to get these values, 1097.71. So there's some time where in between, and we're going to call it B, where we find our max. We want to know when is the amount of water the greatest. So this would be our max. And so I'm going to say, all right, well, where do we find our max? When W prime of t is equal to, we would have E prime of t when we use the FTC here, and we're going to use FTC here. So we're going to have E prime of t minus L of t. And we're going to want to know where is that equal to 0, because we're not concerned about it being undefined because t would have to be negative for E of t. And the same thing is true with the L of t. That's not going to be a problem either because that's the square root of t squared plus 9 on the bottom. That's not going to be a problem either. So we're going to get a calculator out, and what we're going to do is we're going to put this in as y1, and we're going to put the whole expression in as y1. But remember, you're going to have to put it in as 30, let me do it like this. Y1 is equal to 30 over x, the quantity x plus 1 to the 5/4 power, and then that's going to be minus L of t, which is going to be 25x over the square root of x squared plus 9. So when you do this with your calculator, here we have that in there already, boom, and here's what it looks like. And you might have to turn your iPad or your whatever. I'm going to turn it up a little bit. So right now I'm looking at, here's my function. You can see up in the upper left-hand corner, I can't zoom in on that, that's my function. I just typed it as y1, and then you can see if I'm going to tap on the function here, it looks like the x value is about 1.4. So what I'm going to do is I'm going to use my second trace button that I have here, sort of like an 84, and then it's going to ask for a left bound, and I'm going to say 1, enter, and then it's going to ask for a right bound. I'm going to say 2, enter, and it gives me, the 0 is 1.354, which gives us the answer for the problem. Let me go back here. So our answer would be at b is equal to 1.354. Now this is our t is equal to the b value there, 1.354, and that would be minutes. And then I'll leave it up to you. You can check that value in the integrals as well. You get 135.836. Okay, and that would be the maximum. We would say there would be a maximum of 135.836 gallons at t equal 1.354 minutes. Okay, so beep, just let that. A couple things to remember before I close out. When you integrate, you accumulate. So think about that as you move from left to right. You're accumulating area. Just kind of a rhyming little thing you can remember. And then, the amount that you have is always a start amount plus an integral growth minus an integral decrease when you're talking about rate ins and rate out. So I hope to see you tomorrow and have a great day. Remember, stay safe, stay healthy, and stay positive. Talk to you soon. Bye-bye.